Hi, I'm Ajay, a PhD candidate in the Stanford Vision and Learning Lab, and this is our paper, What Matters in Learning from Offline Human Demonstrations for Robot Manipulation. Human supervision has been at the heart of some of the most significant and unprecedented advancements in fields such as computer vision and natural language processing. Large-scale human-labeled datasets have enabled autonomous machines to reach near or even superhuman performance on decades-old problems, such as image recognition and question answering. Roboticists have also been able to make use of human datasets. For example, human operators can teleoperate robot arms using devices such as VR controllers or smartphones to collect datasets consisting of robot arm trajectories, and robots can learn manipulation skills from these datasets. Despite these advances, human datasets have not been nearly as disruptive in robotics as in other domains. There's still a large gap between robot and human manipulation capabilities. Why haven't large human datasets addressed this gap? Is it the ability to collect large amounts of data from humans? While this can be challenging, we do have the means to collect large data sets from humans today. In fact, recently, researchers have been able to develop scalable mechanisms to collect thousands of task demonstrations from humans. The real bottleneck seems to be in learning from human data sets. There's a large gap between what humans can demonstrate today and what robots can learn. On the left, you can see an example of the intricate behaviors that over 50 people demonstrated on this laundry unfolding task. But the robot could only learn simple, limited behaviors from this data, such as unfolding the corner of a towel. Unfortunately, learning from human datasets can also be difficult for simpler tasks. When learning from this crowdsourced pick-and-place dataset, for example, prior work was only able to achieve a success rate of 30%, and baselines fared even worse. In other words, there's a substantial need to understand how to learn from large human datasets. In this work, to fulfill this need, we conducted a systematic and extensive study in order to explore several relevant factors in learning from human datasets. Our study resulted in general insights useful for realizing the promise of supervision and culminated in our RoboMimic framework release, allowing everyone to reproduce our experiments and build on top of our code and datasets. While we explored several factors in our study, in this talk I'm going to organize what we explored into 4 categories. First, I'll discuss how we designed our study. Next, I'll discuss a few challenges that we were able to address, at least partly, leading to improved performance on existing human datasets. Then I'll discuss some insights from our study that made us optimistic about using large-scale human datasets to bring us closer towards human manipulation capabilities. Finally, I'll discuss some open challenges that we identified empirically. These are important for the wider machine learning and robotics communities to work on. There are many relevant factors to consider when studying the setting of learning from demonstrations. I'll discuss 2 factors on the data side and 2 on the learning side. On the data side, what tasks does a supervisor demonstrate? And who provides the demonstrations? On the learning side, what algorithm is used to obtain a policy from the data set? And what does the agent get to see when making decisions? Our study explored these factors. It consisted of 8 tasks, 3 kinds of supervisors, 6 offline learning algorithms, and 2 different observation spaces, allowing us to analyze several important challenges. Our tasks were chosen to test a broad range of manipulation ability. Lift and can consist of pick-and-place motions. In the square task, the robot needs to fit a square nut onto a peg, which is more difficult due to the precision needed. In the transport task, 2 robots must work together to retrieve a hammer and transport it to the other side. This is challenging due to the multiple stages, each requiring different levels of coordination. Finally, we have tool hang, where a robot must assemble a tool stand and then hang a wrench off of it. This is the hardest task. It has multiple stages that each require precise and dexterous rotation-heavy movements. We collected data from 3 kinds of supervisors in this study to isolate what makes learning from single and multi-human data special. Machine-generated data consisted of mixed quality data from RL agents and provides a comparison to common datasets in batch RL. Proficient human data is collected by a single human. This is common in imitation learning. The multi-human datasets are collected by 6 humans of varying proficiency, similar to crowdsourced data. Here's an example of the machine-generated data collected by RL agents. It contains a mixture of good and bad behavior, but this data is very different from what different human supervisors provide. Here's an example of multi-human data. We had 2 worse operators, 2 okay operators, and 2 better operators, resulting in mixed quality data. Notice how the worst data contains mistaken grasps and not noisy robot motion compared to the better data. We evaluated 6 offline learning algorithms in our study. 3 imitation, and 3 batch-RL. The 3 imitation learning methods are behavioral cloning, BC with an RNN network to model history-dependent reasoning, and a hierarchical variant of BC, all of which have been applied successfully to human datasets in prior work. We also evaluated 3 state-of-the-art batch-RL algorithms, BCQ, CQL, and IRIS. To study the effect of observation space, we trained 2 kinds of agents, low-dimensional agents that have ground truth info and image agents that receive raw camera observations. We also studied the effect of pixel shift randomization, which has proved effective for training image agents before. Now let's discuss some challenges that gave us useful insights for learning from human datasets. These insights will allow us to learn better by accounting for how human supervisors make decisions and by choosing what the agent gets to observe carefully. We realize that humans are not perfect Markovian agents. In addition to what they currently see, their decisions may be influenced by other external factors, such as the history of the actions they have provided so far, and the kinematics of the teleoperation interface. How can we account for this? In our study, we saw that history-dependent models can be an extremely effective way to deal with this challenge. To show this, we compare the success rate of BC, shown in blue, and BCRNN, shown in orange, across the square and transport multi-human datasets. BCRNN outperforms BC by up to 55%. Another challenge is that learning proficiency depends greatly on agent design decisions. For example, the choice of robot proprioception requires careful design. There are several potential options like end effector poses and velocities, shown in blue, and joint positions and velocities, shown in green. We observe best agent performance when including only the end effector poses. When trying to add end effector velocity information or adding joint angle information, the performance dropped drastically. This is the difference between working and not working in many cases. How to instrument cameras and use their images is also an important consideration. We found that including both the front view and wrist view camera image and using pixel shift randomization perform best. When trying to remove the wrist camera or the randomization, we see that performance drops drastically. Both are crucial for training good visual motor agents. This shows that the choice of observation space is incredibly important. In our study, we also evaluated the importance of hyperparameter selection when training agents from human data. This slide shows a very small subset of what we explored, but the main takeaway is that even simple algorithms like BC can require careful tuning. In fact, we found that a carefully tuned BC implementation can be very powerful, and that there's hope for scaling simple algorithms. For example, we took our study insights and applied them to the crowdsourced pick-and-place dataset from 2018 that I mentioned at the beginning of the talk. We were able to more than double the state-of-the-art performance, and this was done by using BCRNN, a simple algorithm that we tuned carefully with our insights on our other datasets. This result speaks to the generality of our results. This was a different robot arm, different action space, and different human supervisors. Our study actually resulted in many more reasons to be optimistic about learning from human datasets. One question we studied is how task performance depends on dataset size. Intuitively, more demonstrations means that a larger portion of the relevant state and action space for learning a task can be covered by the data. But what does this dependence look like empirically? For each task, the bar chart shows how performance changes going from 20% to 50% to 100% of the data. Simpler tasks like lift and can require just a fraction of our collected data to learn, while more complex tasks like square and transport benefit substantially from adding more human data. This suggests that more complex tasks could be addressed by adding more multi-human data. Furthermore, we were able to train a proficient image-based agent on our hardest tool hang task without any hyperparameter tuning by applying the insights from exploration on the other tasks and datasets. Moreover, we were able to directly apply our study insights to real-world manipulation. These BCRNN policies were trained using 200 human demos without any hyperparameter tuning. We report the final policy checkpoint performance instead of the best one, since evaluating all policy checkpoints on a real robot is infeasible. So this is the lower bound. Most of the tasks are close to simulation performance. We also saw that as in simulation, both wrist images and pixel shift randomization are crucial for good performance. After conducting this study, we were convinced more than ever that studying the setting is worthwhile and promising. To recap, we were able to start learning proficient policies from large human datasets, show that collecting even larger human datasets is worthwhile. We were able to solve difficult visual motor tasks using our study insights, and finally see that insights can transfer to the real world. This motivated us to build and release the RoboMimic framework, which contains datasets, implementations of learning algorithms, and a modular structure that's easy to build on. We're incredibly excited to see how this facilitates progress in the community, and I'll ask tackling open challenges as well. Let me now discuss some of the open challenges that we explored. One challenge is that learning effectively from suboptimal human data remains a difficult problem. We confirmed this empirically. While BatchRL has proved to be a powerful tool for learning from suboptimal machine-generated data, it performs very poorly on mixed quality, suboptimal multi-human data, up to 65% worse than imitation learning methods. A second open challenge is related to a difference in supervised learning and imitation learning. In supervised learning, validation loss is a good indicator of model performance, but in imitation learning, validation loss corresponds poorly to a policy's task success rate. This makes it hard to know which trained policy checkpoints are good without trying out each and every model directly on the robot. We empirically validated that this is an issue by trying to use validation loss to select a good policy checkpoint. We compared it with the true best policy shown as Oracle. The significant gap in performance shows that improving offline policy selection is an important problem for future work. Open challenges like these are of broad interest to the machine learning and robotics communities. They relate to general problems, such as dealing with imperfect supervision and selecting good models without deploying them. RoboMimic will allow studying these problems grounded in a robotics setting. We're really excited about how we can make progress towards the kinds of tasks we want our robots to be able to do by addressing some of these open challenges and learning from human data. Our study allowed us to make some progress, but there's still a long way to go. We're also excited to see how our RoboMimic framework facilitates this in the community. I highly encourage everyone to take a look at our RoboMimic datasets and framework. The simulator we used, Mujoko, is now completely free, so check them out. Thanks a lot for listening, and I'd be happy to take questions now.
Okay, yes, there's another question here.
Hi. So I was interested in the second part of the talk. You were showing the graphs about the tasks that were transferring from simulation to reality. And there was one that was dropping to 3%, like the tool hanging. I think it was tool hanging. Do you know, so can you share, like, why do you have insight why it was not transferring? It was like because it was too precise, I don't know.
Yeah, so that's a great question. Thanks for the question. So to clarify, when we're talking about sim to real transfer here, we're actually, these, the real robot results were basically an identical setup to simulation, right? So we collected 200 human demos on the real robotic platform and then trained agents using hyperparameters that worked well in simulated domains, right? So one cause for this gap can be that, with further tuning, there's actually a hope to do better. But the tool hang task was the hardest task that we looked at, and it had the highest precision requirements. And there can be additional sim to real differences in terms of the modeling and simulation versus the one on the real robot. And the real robot task can be significantly harder in terms of, the low error tolerance that's required to actually solve the task successfully. That's something that's notable and different compared to the other tasks like lift and can, and even the peg and hole, the square nut assembly. So there's actually a lot of reasons that this could be a lot more difficult on the real robot.
So just to be precise, like, is it because, so the policy was like executed open loop, there is no feedback?
No, there is feedback. It's closed loop, right? So we took 200 demos from the real robot. We trained a behavioral cloning agent on the real robot as a closed loop policy running at 20 hertz, right? Using camera observations, RGB observations on the real robot, identical to what we did in simulation. And then we deployed it. So it is still closed loop, but the amount of error that can be tolerated can be much lower. And the real robot platform actually presents other challenges that are orthogonal to simulation as well, right? In terms of observation delays, right? In terms of not ensuring that in simulation, everything happens clocked exactly at 20 hertz. And on the real robot, there can be different, there can be stochasticity in how often you're applying actions and how often you receive observations. This can compound with issues in imitation learning, like covariate shift, and make it very difficult to learn high precision manipulation. So we could be seeing some of these effects here.
There's one more question here and one more in the chat. Let's do the room first and then the chat.
Thanks. Along the same line of what we just discussed, what is the procedural variation in your set of tasks on the initial position of the props and in general also on the diversity of the task itself, not just the initial condition, but perhaps the dimension of the props, the location of the boxes and so on?
Yeah, that's also a great question. We have videos of this on our website, and I'd be happy to share more during the poster session as well. But there was definitely variation in things like the object poses, in the transport task, the location of the bins varied a little bit. For example, in the pick and place can task, the can was allowed to vary anywhere inside the bin. For the lift task, the initial position of the cube, varied in a square box. For the tool hang task, we had some variation in rotation and position for the tool, for the base. Sorry, it's a little hard to describe verbally, but we did have variation in both the object poses for the initial conditions and the initial robot arm as well, a little bit of variation.
Thanks.
And yeah, I'd be happy to share more during the poster session, and you can also take a look at our website.
Great. And finally, we have a question in the chat. This is from Yanran Wang at Imperial College London. And the question is, in the learning-based methods like imitation learning and offline reinforcement learning, how do you consider or guarantee safety? And they give some sort of, I guess, more concrete metrics that they're interested in: stability, explanation, perhaps, or robustness.
Yeah, that's an awesome question. I think especially, in this study, we focused on end-to-end learning methods, and there it can be a lot harder to guarantee safety. And actually, there's a rich body of work that's been looking into things like this, safe imitation learning, safe reinforcement learning, and guaranteeing that, when you visit a state that's out of the distribution of data that you've seen, can you terminate? Can you avoid going back into that distribution of states? We haven't done that work here, but I think there is promise for going forward for ensuring safety. But it is very much an open research problem.
Great. And I'm not sure how we're doing for time. We do have one more short question. Perhaps we can have this one answered quickly. So Pete Florence from Google Robotics asks, for the offline RL methods, did you also try to give them sequence models, RNN-like as well, or only for the behavioral cloning method?
So that's a great question. I'm actually looking forward to trying some more recent sequence-based models because there's been a lot of recent work that has showed some promise. But for this work, the IRIS baseline that we had, the IRIS offline RL algorithm, did use an RNN for the low level. It's a hierarchical algorithm. So there is actually some, primitive, I would say, sequence modeling going on there. But certainly there are, more sophisticated methods that are coming out these days. People are starting to apply things like transformers to RL and IL. So there's a lot of excitement on our part for trying these different types of models and seeing how we can get even better temporal abstraction in combination with, some of what these offline RL algorithms do on suboptimal machine-generated data. Maybe we can unlock some of that potential for human data as well by combining these.
Excellent. Thank you so much, Ajay. So, Rudolf, I'll pass it on to you. I don't know if there are any last minute burning questions, and otherwise I think we can move on.
Yeah, I think so. Yeah, I think we should go to the next presentation in interest of time. Yeah, thanks the speaker again.